All right, guys, we're almost finished with discussing what a method actually is. And in the next portion of the video series, what you're going to find out here in the next handful of minutes is the remaining maybe pieces of the method. Again, we're going to quickly go through some of these, and we're not going to focus on details, just overview of what they are and why they're here. And the next part is sample collection, preservation, and storage. So this is really for those field collectors. Remember, this is the EPA. The EPA is probably going to go out in the environment in some form or fashion, collect water samples, soil samples, air samples from a dedicated or determined site, and they're going to bring those samples back into the lab. So, for instance, not everything will have a sample collection, preservation, and storage, but you could, depending on what the material actually is. So in section 8, I want you to think of, if I'm working at a company like CFPUA, let's say that it's going to be my job for the day to go out and go into the field and collect the samples for the lab. Sometimes they get their lab workers to do that. I mean, just to change up their days and stuff every now and then. Okay, so 8.1, sample collection, dechlorinization, and preservation. So it's saying collect all samples in duplicate. If samples such as finished drinking water or wastewater are suspected to contain residual chlorine, we're going to add 25 milligrams of ascorbic acid per 40 mils of sample to the sample bottle before we fill it up. And if the residual chlorine is likely to be present over a certain amount, then we might have to kind of do something else a little bit differently. So again, this is part of the SOP, it's part of the field directions, and this is what the field collector would follow when they would go out and sample or collect these particular soil, again, water, air, before they bring it back into the lab. And for this particular method, it's all about water, wastewater, okay? Next up, 8.12, 8.13. Again, when sampling from a water tap, we want to open it up, allow the system to flush. 8.13, when the sampling from an open body of water, you want to make sure that you collect it in this type of beaker or this type of bottle. You want to make sure that this is what you add to it. You want to take a look at your pH range. The pH range should be about 2. So you add some acid until you get down to that moment. 8.14, 8.15, the samples must be chilled to 4 degrees when you collect them and maintain them at that temperature. 8.15, if a sample foams when HCl is added, discard that sample. Collect a set of duplicates, but don't acidify them. They have to be flagged as not acidified and kept in the refrigerator or below as far as temperature goes. They also have to be analyzed within 24 hours after you collect them. So this is directions within a SOP. That SOP would be given to the field collector, and it would have very limited things on that SOP, and it would only focus on the collection, preservation, and storage of those particular samples. That is it. That's all the field collector cares about. Why does the field collector want to know SOPs on all the lab directions? That's not their job for the day. That's not their responsibility for the day, so they don't need it. So what you're going to find out is that there's going to be multiple SOPs that can come from only one method, and that is perfectly normal. So we would have an SOP for our field collector, we would have an SOP for our lab worker, we could have an SOP for our glassware cleaner, we could have SOPs for a number of different roles that have responsibility in this particular types of method. All right, and those people would get those SOPs only and not worry about the other SOPs because they're not performing those jobs. So why do they need to know directions on how to do those particular types of jobs, right? So more than one SOP can come from one individual method, and that's something that we have to remember because it is pretty common for companies to do that. Also, I want you to keep in mind that in terms of SOPs, everyone has an SOP. That does not mean that everyone in a lab has SOPs. That means all areas of a company has SOPs. All the way down to the custodial staff folks. They will have an SOP on what they need to do in order to clean the hallways, how to clean the windows, how to clean off the countertops, how to clean the bathrooms, how to sanitize things. they will have SOPs built for that. So SOPs are going to be involved in all areas of a company, not just within the laboratory related workspaces. All right. 8.2 is sample storage. Here it says less than 4 degrees, blah, blah, blah. 8.3 says filled reagent blanks. And it says, okay, remember that definition? Ding, ding, ding. We talked about definitions of methods, and filled reagent blanks were one of those. Lab reagent blanks were one of those as well. So we talked about the purpose of these. It also gives the field collector some information about how to handle some of those. And then 8.32, use the same procedures used for samples to add ascorbic acid and HCl to the blanks. If the same batch of ascorbic acid and HCl should be used for the field reagent blanks in the field. So this is an idea, again, that if we're going through these extra steps when we get samples out in the field, then our blanks should really be following the same exact process. So the blanks, even though they're blanks, they have to be exposed to the same types of things that our samples are. From the very beginning, from the collection all the way through the processing, through running them on the instrumentation. They really do have to be exposed to everything that a sample would see and touch and feel throughout the time. Next up is the quality control section of the EPA method. This is where, of course, all of the QC requirements are going to come into play. So everything from the signal, everything from what we should be making, how many should we make, how should we handle the data that comes from it, all of this is going to be built into the quality control section. And of course, this is where the QC department would really pay attention to, because they have to make sure that quality is embedded into the method. And they have to make sure that all of these are checked off. So for instance, 9.3. Initial demonstration of laboratory accuracy and precision. Analyze 5 to 7 replicates of a laboratory fortified blank containing each analyte of concern at a concentration in the range of 0.2 to 5. So we're going to have to make something. The quality control department's going to have to make something. We're going to have to make sure that everything that we're looking for is present in this something. And this something is the LFB, the lab fortified blank. And then we're going to run it 5 to 7 replicates. So we're going to take this sample and we're going to put them in separate containers, and we're going to run one after another, after another, after another, after another. And then this will allow us to get an average, and it allows us to get a standard deviation. This helps us to determine our average accuracy and our standard determination, which is our precision. So these are extra things that the QC department would go through in order to make sure, yeah, my method looks good, my equipment's working the proper way, my lab workers are preparing things the proper way. Everything is smooth like butter. So let's just keep on cranking it. Let's keep on churning it out. And I think that will be pretty good as long as these types of things are still upholding throughout the analysis run. Okay, so it goes through and it tells the QC department on some of these thresholds, some of these requirements that they would need in order to pass what we would call a batch. So for instance, for each analyte, the mean accuracy expressed as a percentage of the true value should be between 80 to 100%. So keep in mind that windows are always a thing here for laboratory data. We are not really looking for what we call exact data. Exact data, we don't want it to be exactly what it should be. We know there's error. We know there's contamination. We know there's problems throughout the time, and that's never an issue. Quality control knows it. Methods know it. Regulatory agencies know it. That's not a big deal. However, we need to make sure that we fit within an ideal working range. And that ideal working range in this particular case is 80 to 120%. And that the relative standard deviation, keep in mind, what did that mean? Relative standard deviation should be less than 20%. So this is actually percent RSD. They didn't say percent RSD, but I know that it's percent RSD because they gave me that value in terms of percentage. So that's my standard deviation divided by my average times 100. We talked about that in the stat section, and here it's showing back up, and that's one of the reasons that we talk about it, because they are built in the methods that quality has to follow to make sure we got legit data that comes from the instrumentation and the lab method. As I continue on, you're going to see multiple areas here for quality control. It is often a beefy section, and that's because all of these definitions were all quality control samples in a way, and we want to make sure that we give credit to as many of those quality control samples as we can. What passes, what fails, how should we handle them, how should we make them, and so forth. So, for instance, 9.8, at least quarterly, replicate LFBs should be analyzed to determine the precision of the lab measurements. Add these results to the ongoing control charts in order to document the data quality. So not only are we looking at what's going to happen for that particular day, but most of the time this method is going to continue throughout the year at these companies. It's going to be a common test that they might do. And if it is, then we want to keep track or a database of everything that we are seeing on our end as far as these samples go. So it helps me kind of predict some of the problems that might happen with equipment later on down the future. When is something going off? When is something messing up? So that way we can catch these problems and fix it before that time actually arrives. Section 10 is calibration and standardization. So again, calibration and standardization is all about this idea. I'm going to make a cal solution, and that cal solution has a known concentration, and that is going to relate to a signal. So it's this concept that a signal is going to get generated. What does that signal actually mean? I know the higher the signal, the higher the concentration. Good, got it. But if it gives me a particular value, what does that correspond to concentration-wise? And let's see how close we can get that concentration mathematically. So that's the purpose of the calibration solutions. And there's a whole section here that's dedicated to calibration and standardization. Keep in mind that cal solutions typically are going to be 5 or more, and 3 is going to be the minimum that we would ever see in a method. We cannot go lower than 3 at all, but preferably 5 or higher is where we're going to target. Calibration also includes any type of internal calibration that the instrumentation has to make on itself. So not only just my cal solutions, but also let's calibrate, let's make sure that the instrument is reporting 0 when I tear it out. Let's make sure that the instrument is giving us an absorbance or a signal of 0 when nothing is going through it. So those specifics, though, are not going to be detailed too much in here, because that's really dependent on your equipment and your instrumentation. But you're going to find at least mentioning calibration of the machines in this section if the method has an instrument that it's using. All right, so as I scroll through, that's what you're going to be seeing. As I keep going, it says continuing calibration checks, all of these other cal solutions that need to be in the mix. How can we make sure that our line is actually a line? What value do we need to go to as far as R squared value goes? All of that is going to be section number 10 for calibration and standards. Next up is our finally procedure. This is where most of the SOP is going to be built. This is what laboratory workers would see most of the time. They don't really see anything prior to this because they're letting their method developers take care of that, and they're letting their method developers adapt that information into an SOP to create their own directions for their laboratory workers. But very large portion of procedure section from the EPA or from any method, this is what would be seen to the laboratory worker that's doing the test. So sample introduction and purging, everything from how we handle the sample, how we set the instrumentation settings, in this case, temperatures and flows and all of that kind of stuff. It's going to be detailed in here for a lab worker. Think of this as like, what temperature do I preset my oven on? I mean, those are the types of things that we're doing here. As far as sample processing goes, how to process the sample, how to clean the sample up, what do I need to do in order for like filtration, digestion, heat it up, cool it down, what goes on. So that's going to be part of the procedure section for an SOP writer. Next up is data and analysis. So this is going to give us some ideas of how to handle some of the calculations. So again, they try to not make any gray areas. They're going to specifically lay out equations. They're going to tell you exactly what you need to do with the concentrations. And for the most part, this area is taken care of at a company by a spreadsheet. So this is going to be an Excel or Excel-like spreadsheet where you're going to key in your raw data, and the raw data will then be handled by the spreadsheet, and it will go through and it will calculate everything that it needs to calculate for you, so that way you don't have to worry about it. Those calculations are embedded because they want to make sure that things like this are taken care of the proper way. And they don't want you to make mistakes. They don't want you to put in values into a calculator, key them in the wrong way, and provide wrong data. So they're going to build these templates, and you're going to be keying your raw data most of the time into these spreadsheets and allow the spreadsheet to do all the math work for you. It makes it very simple, makes it very easy. So that way I just have to key in one number, and that is it. And the spreadsheet has already been validated. It already knows, yep, we're going to handle our data the proper way. And it locks you out most of the time of everything in the spreadsheet except the cells that you can actually key in numbers for. That way you cannot make accidental changes to the spreadsheet, which will then modify or give you wrong results for a reviewer. Next up is method performance. So it's all about this idea that once the method goes forward, how do we ensure that it performs the proper way? What do we need in order to make sure that we can see what we can see? How low can we go? What kind of regression lines do I need? This is kind of that section and what it's for. Next up is pollution prevention. How do I make sure that I'm not contaminating the room or contaminating the atmosphere when I do this particular method? Next is waste management. So this is the idea that I'm going to be using solvents, and I'm going to be using maybe cancer-causing agents here in this particular method. So what do I need to do in order to get rid of it? Like, can I just dump everything down the drain and be okay with it? Or do I just put it under a fume hood and let it evaporate and be okay with it? That's the purpose of the waste management section. Next up are the references, and this is how the original method was built. And over time, it could have had revisions. So why did those revisions happen? And what kind of reference material did they use in order to make those judgment calls to give you newer versions of the same method that might perform a little bit better? The tables, diagrams, flowcharts, and validation data at the end of a method is typically always here for convenience. So that way it gives you a whole list of things that you could be looking for in this method, and it tells you a little bit of chemical information from it. So this particular table tells me the molecular weight of the compound. It also tells me like primary quantitation ion, secondary quantitation ion, whatever that means. You will eventually know what that means later on in the program in a different course. But it gives me some chemical literature that I can go by at least in order to make these judgment calls of things that I would see in a laboratory or on a report. As I scroll through, it is also pretty common to get report data. Like, this is what we typically see. If this is what you're looking for, this is where it comes out. This is how much will come out. This is typically the trend that's happening with these individual analytes that we are analyzing and running. It also gives me sometimes examples of chromatograms or an actual report when we start to see multiple numbers or multiple components coming through. So that's not uncommon either. You'll also see some diagrams if it requires some type of glassware, some type of setup that we would have to do in the lab. Very often, if you just read directions, it's very complicated to kind of understand or comprehend what they're asking for. And for that reason, there's also some diagrams that can be included here on the back end of the method to kind of tell you this is what we mean, this is what we're referring to. Here's an example of some report data that's coming from a typical sample. So that way I can see, is mine kind of looking like this? Or maybe a report from a standard, is mine looking like this? That's the reason that these resources are here on the back side. All right. So a couple of things with the methods now. First are interferences. Again, this is something that disrupts the measurement, and many things have interferences, but some actually have no interferences at all, and you won't see anything in that section, period. Next up, we saw the safety section. The safety section was all about how to handle the samples safely, how to handle the standards safely. So we don't want you to poison yourself. We don't want you to send yourself to the hospital. So that section is going to be in here for method developer or reviewer. The other section we saw was equipment and supplies. So keep in mind, this is all the containers, the tools, and the instrumentation. It has nothing to do with reagents. So all of the hard pieces that are going to be required for the laboratory method. You're also going to find all the washing and cleaning steps. So glassware washing is a very important job. I can't stress that enough. A lot of people think that if they're assigned to wash glassware in a laboratory, it's like the skank of the jobs, but it is not. It's the most important job in a laboratory because everything has to be cleaned, everything has to be sanitized, everything has to be ensured that it brings no contamination to the table. So glassware washers are the most important role for that. And there are companies that will just hire glassware washers. That's all that they do all day long because they are trained in the proper ways to do it. So don't turn your nose against those types of jobs. Those are just as important as everything else, okay? Next up were the reagents and standards. This is the area where it talks about every liquid solution that I need, every solid reagent that I need, what do we need to order, what type of chemical compounds are going to be required for this method to go forward. It gives me what we call purity grades. Keep in mind ACS is the most important, ACS is the cleanest, ACS is going to be some of the best reagents that are going to be out there for us to order from. But it also talks about how to prepare some of the standards that are going to be required for the lab method. Next up, we saw sample collection. Again, it's all about how do they go and collect them? How do they transport them? The idea of duplication, the idea of keeping it cold, keeping it froze, putting some acid in it, preserving it. All of those details, every bit of them are going to be included in the sample collection section. Quality control, we said these are the QC parameters. So we're going to see a lot of our acceptance criteria stated here. So that way, if our quality control samples are meeting lab expected data, then our samples we feel really good about, and we can end up passing those and passing what we call the batch of samples that we've ran. Next up are calibration and standards. So how to build the cal curves, what we should be looking for, what some of the requirements for those once I go in and start building these and generating them. Finally, we get to our procedure. This is our actual SOP steps. So this is what most people will see, but keep in mind the method has been adapted slightly to make the SOP from. So these are just the highlights and the most important parts of the procedure step. Toward the end, it's the data analysis piece. How do we handle the math? The method performance piece, all about accuracy, precision, method detection limits. How do we prevent the pollution? What should we watch out for when we do the actual lab? Once we're finished with it, how do we get rid of it? So anything that I need to know as far as waste goes. And then finally, the references. How was the method built? And the tables. Examples of typical reports that show up if I do this method the correct way. All right. So that is going to stop our method discussion. And after this, we're going to dive a little bit deeper into what we call a standard operating procedure or an SOP. So now that we have this idea of where the SOPs originate from, the methods are coming from these regulatory agencies. I need to look at those, see what's there. Now we need to take that and actually customize it for what we do in our own lab facility. Are there any things that we need to talk about as far as SOP is concerned that we need to highlight and that we need to mention? So that's what we're going to do in the next portion of the lecture video series. We're going to turn away from the methods, and now we're going to look at SOPs and some of the regulations that fall within the SOP category. What to watch out for, why we have to give them to you, why you should have them, why you should follow them. So that's what we're doing. Next up, Now's a great time, though, to take a break if you've not taken one already. Now's a great time to finish some of those method assignments that you're seeing within Canvas or the online course. Go ahead and take care of those, finish those out, answer those questions, and then the standard operating procedures can happen a little bit later into the future.